Welcome uh, and hello to all of you. This is the second tutorial, and in this tutorial we will discuss some problems related to the topics that we have covered in week 2 of thin film deposition module. Okay, week 2 of thin film deposition was uh, dedicated to plasma and plasma physics and our thin film deposition process called sputtering. Okay. So, we will solve couple of problems to help you understand this week 2 lectures content in a better way. Okay. This is our first problem. It states that we have a parallel plate plasma reactor, okay, with 60 centimeter diameter. Electrodes contains an argon gas at 20 Pascal. Okay. In plasma, the electron temperature is 2 electron volts, while the ion and neutral temperature is 0.03 electron volts. If the plasma density is 10 to power 16 per meter cube, then we are asked to calculate mean electron velocity, Debye length and degree of ionization. Okay. So, we will start by solving first part A. Okay. We know that electron temperature, now this is given in the units of energy, right, and this relates to kb into T. Okay. So, the temperature is T, but since kb is a constant, we can call this this energy also the temperature of the of electron. Okay. So, this is essentially of the energy of the electrons. Okay. And if we know that this is the average energy of the electrons, then this should result this will be due to their kinetic energy, right. So, we know that this energy will be equal to half mv square. Okay. Now, and this is kinetic energy of electrons. By solving this, and we know that we can write this in terms of joules as such, and 1 by 2 mass of electrons is 9.1 10 to power minus 31 kgs, and v square. We can solve for v from this. V is equal to 8.38 into 10 to power 7 centimeter per second. Okay. So, this is my mean electron velocity, because this is the average average energy. So, we will get a mean average velocity. Okay. So, this is part A, very simple. Now, for Debye length, we had discussed an expression which is for Debye length, it is epsilon 0 kBT divided by Ni q square. Okay. Where epsilon 0 is permittivity of free space, and this equals to 8.85 into 10 to power minus 12 farad per meter. Okay. kBT, again it is reported as temperature, but it is the energy, right, and Ni is the density of ions. Ni is density of ions in plasma, and this is also equal to plasma density. So, this is also given to me in problem. So, this is my plasma density. Okay. Q is the charge, okay, which is 1.6 10 to power minus 19 coulombs. Okay. Now, since this is kBT is temperature, which temperature should we use? Is it electron temperature or the temperature of ion and neutral species? If you recall, this Debye length is a length scale over which the charge is screened by the electrons. Okay. So, if you put a positive charge in plasma, the electron cloud will be around it because of Coulombic attraction, and it will shield the effect of the potential due to this positive charge. So, it is the electron cloud, right, whose energy is important to calculate this Debye length. So, this T or KBT would be electron temperature. Okay. And since we know all the we have all the information, we can calculate this value, and if we calculate, this comes out to be around 1.05 into 10 to power minus 2 centimeter, very small. Okay. So, this is my electron mean electron velocity and Debye length. Okay. Next part is to calculate degree of ionization. Okay. Degree of ionization in a plasma is given as number density or density of ions in plasma divided by density of ions plus neutral species. Okay. So, we need to calculate these two values. Now, we know that temperature or KBT of ions and neutrals is given as 0.03 electron volt. Okay. Using Boltzmann constant, if we convert it to, let me see, the Boltzmann constant is 1.38 into 10 to power minus 23 joule per Kelvin. Okay. And from this electron volt we can convert it to joules by multiplying by this. Okay. So, from this we and using the value of Kb, we can calculate the temperature of ions and neutrals species, which will be equal to 347.8 Kelvin. So, this is the temperature. Okay. Now, we are given a pressure of 20 Pascal or 20 Newton per meter square. Okay. This is the SI unit of pressure. Okay. And we also know that PV is equal to nRT, okay, or P is equal to N over V RT. So, given P and T, we can calculate N over V. R is gas constant, it is R is equal to 8.314 joule per Kelvin mole. Okay. So, since this is in mole, it will give you this N over V is equal to moles per volume. Okay. So, we can calculate N over V using this, we know R, we know T and we know P. Okay. And we can also convert this N over V if we multiply it by Avogadro's number to number of atoms or molecules per unit volume. Okay. And this, upon solving, it comes out to be 4.16 10 to power 21 atoms per centimeter cube. Let us use atoms here also. Okay. So, this is the total number of ions and neutrals. So, this is my or the density of ions plus neutral species in plasma. Okay. Now, if you look at this degree of ionization is equal to density of ions density of ions is also your plasma density, which is equal to sorry, this is meter cube, sorry for this mistake, this should be meter cube, okay, because we are using SI units here. So, we will get in meter cubes. Degree of ionization is density of ions is also plasma density, which is 1 into 10 to power 16 ions per meter cube, and divided by density of ions and neutrals, which is 4.16 to power 21 per meter cube. So, this will give me degree of ionization of 10 to power minus 6. So, this is my degree of ionization. Okay. So, this completes my first example of on plasma. Please keep in mind what temperatures we are using, okay, right, and temperature relates to the energy. Okay. So, these two aspects are to be kept in mind, and it is just by substitution into various equations that we already know, we can solve these equations or solve these problems. Okay. Now, let us look at another example. Okay. So, this is again an example based on magnetron. Okay. If you recall, in magnetron we use perpendicular electric and magnetic fields to confine electrons in certain area or certain region, so that they are not lost, okay, and they ionize more and more gas atoms or molecules to sustain the plasma. Okay. So, we have a DC planar, so we have a DC planar magnetron with cathode and anode spacing of 10 centimeter. Okay. So, this is my configuration, this is cathode and anode, and this is DC, and this is 10 centimeter. Okay. And a potential difference of 1000 volts is applied. Okay. So, if I have somewhere here, this is 1000 volts. What should be the magnetic field to confine electrons within 0.5 centimeter of target, or which is also cathode? Okay. Now, I want my electrons to be confined within 0.5 centimeter. So, suppose this is 0.5 centimeter. Okay. Now, we know that electric field is in this direction, okay, and we want to confine electrons within this. So, my magnetic field should be in perpendicular direction. Okay. So, let us say that my magnetic field is in this direction. We need to calculate what should be the strength of this B, so that my electrons do not move out of and of course, electrons being negatively charged will tend to move towards positive electrode. We want to confine these electrons within the distance of 0.5 centimeter. Okay. Now, we know that magnetron works on the basis of Lorentz equation, okay, where my force on electron is given by Q V cross B plus Q E, right. Q is the charge on electron, E is electric field, V is the velocity of electrons, and B is the magnetic field in perpendicular direction. Okay. Now, we know E, we know B, but we do not know V, right. So, how do we solve this? Recall that suppose there is B present, okay, velocity of electrons will be in this direction, right. So, electron will be accelerated. So, each electron starts at 0 velocity and is accelerated in this electric field, okay, and it attains a velocity of V at this point. So, V is because there is a constant force. So, the V is the velocity at this point and in this direction, okay, and if my magnetic field is strong enough to oppose this electric field, right. So, V cross B, so V is in this direction and B is in this. So, if V cross B is strong enough to oppose the force due to electric field, then my electrons will be confined in 0.5 centimeter, right. So, from this we know that these will be two opposing forces. V cross B will be moving in the opposite direction, and E will try to move electrons towards positive electrode. Okay. So, we know that V cross B should be equal to E, right, for electrons to be confined. Okay. Now, since we also know that that can only happen when V and B are the maximum values of this is sin theta is equal to 1. So, this would be V B sin theta is equal to E, and if theta is equal to 90 degree, when V and B are perpendicular to each other, then we will have expression as this. Okay. So, we do not need the arrows for because these are the magnitudes. Okay. Now, we know E, but we do not know the velocity of electrons at this point. Okay. Now, we can also calculate that because we know that the force on electron is electric field by electric field, right. So, force on electron is E, capital E, right, in this direction. Now, this force will be equal to m E and acceleration, okay. And we know that u, which is the starting speed or velocity, is 0 for electron. U is 0, s, the distance travelled, is 0.5 centimeter, and we need to know what is V. Okay. And we are using that, see, the maximum velocity, it can, this magnetic field should be able to rotate such that it opposes this E, right. If the V is smaller than this velocity, then it will continue to accelerate such that V cross B becomes or V into B becomes equal to E, right. So, we need to know the velocity here. These velocities do not matter because they are smaller, okay. These are smaller. So, V cross B will not never be enough to counter the electric field. So, it will, they will continue to accelerate towards the positive electrode, okay. But as soon as they reach velocity V and at 0.5 centimeter, the B cross V value will be equal to E and they are confined. So, we need to calculate this V. Now, from Newtonian mechanics we know the expression that V square is equal to U square plus 2AS, okay. From, and A is F or E over A is E over ME, okay. And so, we know the acceleration, this term is 0, and we know S as 0.5 centimeter, and from this we can calculate V as V will be equal to 4.2 into 10 to power 6 centimeter per second, okay. So, this is my velocity at 0.5 centimeter, okay, because acceleration is only in the direction of electric field, okay. So, the velocity will only be due to the electric field, not magnetic field. Magnetic field, it will provide the force in the other direction where it rotates, but not accelerated in this direction, okay. So, this is an important aspect to remember. Now, since we know this velocity, we know the magnitude of electric field. Electric field is nothing but 10,000 volts divided by 10 centimeter. So, sorry, this is again my mistake, this is meter per second because this is 10 to power 4 volts per meter, okay. This is my electric field. So, we know electric field, we know velocity, and from this we can calculate of magnetic field, which is 0.002 okay, volt second per meter square, which is also called Weber per meter square. Okay. So, we can also say 0.002 Tesla or equal to 20 Gauss. This is the magnetic field we need to have electrons confined in 0.5 centimeter. So, if we have this geometry and you are considering what kind of magnetic field or magnet I should have at the back of my cathode, this is the calculation to solve that. Okay. So, this is my example 2 and I hope you understand how this electron dynamics in coupled magnetic and electric field works here, okay, for a magnetron. Thank you.